All right, well, I think I can start an introduction now. Our colloquium speaker this week is our very own past graduate student and present colleague across the way at Carnegie, Gwen Rudie. Gwen got her PhD at Caltech in 2013. Is that when it was? Was it 2012 or yeah, 2013? I was able to work with Gwen for 6 years. And so during that time, in addition to doing her thesis research, which was very significant, she was also a member of the MOSFIRE instrument team. She contributed significantly to some of the elements of software like the mass design program and the exposure time calculator, and helped with lab testing and analysis before we shipped off to Hawaii. And then of course, she was also involved in commissioning. So Gwen made a very significant mark on instrumentation during the time that she was at Caltech as well. She was a Carnegie Princeton Fellow for her postdoctoral work, and she was rapidly snapped up onto the staff before finishing her Carnegie Princeton Fellowship, and has been a staff astronomer at Carnegie since 2015. She is an expert on the intergalactic and circumgalactic medium, and it wasn't on purpose that we've had 2 talks in a row on the CGM. It just worked out for people's schedules that way, but it's highly complementary to what last week's colloquium speaker was discussing, Ben Oppenheimer. But in any case, I want to welcome Gwen and thank you for speaking under these circumstances, which of course are not ideal. And Gwen's title today is Feedback and Feeding the Circumgalactic Medium of Star-Forming Galaxies at Redshifts between 2 and 3. Take it away, Gwen.
All right, thanks Chuck for that introduction. Can everyone hear me all right?
Yes.
Oh, okay, perfect. So it's wonderful to virtually visit you all and to be back at Caltech, so to speak. I'm really excited to tell you about some of my recent work. In particular, most of my talk will focus on studying the circumgalactic medium of galaxies at cosmic noon, but I'll, towards the end of my talk, touch on some other projects that are ongoing. I wanted to acknowledge my many collaborators on this work. In particular, I'll show work that's led towards the end of my talk by Tom Cooper and Farai Zahedi, who are postdocs at Carnegie, as well as Drew Newman. But much of the work I'll talk about today is work that's been done in collaboration with many names that you'll see on here that are familiar, Chuck, as well as many of his former students and collaborators. All right, so jumping right in. I thought I'd begin with a statement I thought we all could agree on, which is that baryonic processes really control many of the observable properties of galaxies. So while dark matter may provide the scaffolding onto which galaxies are formed, the way in which gas falls into galaxies and the way in which galaxies accrete gas from the intergalactic medium can dramatically impact how efficiently such a galaxy can form stars. Similarly, energetic processes that occur as stars form in these galaxies, we know drive galactic winds, seen down here. And by carrying out mass and metals from these galaxies, this can also impact the forward evolution of galaxies. And understanding these processes is really one of the critical components left in sort of completing a picture or an understanding of how galaxies form and change over time. Now, I've painted this as though it's a linear process, but of course we know that it's not. It's complicated, it's messy, and it certainly occurs across time. And it's often now talked about as the baryon cycle, in which all of these processes occur simultaneously in galaxies. And the important point is really that we would like to be able to trace the flow of gas in and out of galaxies in order to better understand how they're forming and changing over time. Okay, so how do we know that these processes are important at all? So one of the things that's sort of paints this picture well is just looking overall at how galaxies seem to be regulated and how massive they are in general. So here I'm showing a galaxy mass function and comparing it to the mass function of dark matter halos. Now, the very different shape of these two distributions points to important processes that are occurring in galaxies. And in particular, we believe that feedback, energetic processes occurring in galaxies, are particularly effective at making galaxies less efficient at forming stars at both low and higher masses. But we think that different processes are likely occurring at these different spaces. Another observable of galaxies that is often studied is, of course, its overall chemistry and bulk metallicity. So here I'm showing a plot on the right from Andrews and Martini, which shows the mass metallicity relation for galaxies. So we know that the more massive a galaxy is, the more likely it is to have a more significant overall abundance. And of course, we would imagine that the flow of material into galaxies would impact potentially this metallicity. So if, for example, a galaxy accretes material from the intergalactic medium that has lower bulk metallicity than its interstellar medium, then we would expect that to dilute the metallicity of the next generation of stars to form. But similarly, if massive winds from these galaxies carry out metals, and especially if they carry out metals preferentially, then we would also expect an impact in the bulk chemistry of these galaxies. So this is really critical to understand if we want to understand things like the mass metallicity relation, but also for any other field in astrophysics where we're interested in the metallicity of a population, we of course are interested in understanding how the bulk metallicity of galaxies are impacted by these flows. All right, so if we're interested in studying gas flows, I would argue one of the best times during the sort of evolution of the universe to study this is during the cosmic peak of star formation, which happened around a redshift of 2. Now that time I find particularly interesting also because, at least theoretically, it's predicted to sort of be the peak of gas flows. And here I'm showing two sort of beautiful visualizations of these processes occurring in the distant universe. So on the left-hand side, I'm showing simulations from Phil Hopkins and his collaborators that are illustrating the potential effect of feedback on distant galaxies. The right-hand side is instead showing work by Freke van der Voort that focuses more on how galaxies accrete gas from the intergalactic medium. And there's been a discussion occurring over the last decade or two about the potential for relatively cool gas coming in into these galaxies in what are called cold flows, or cold accretion. Now, regardless of exactly what these processes look like and whether these simulations are realistic or not in terms of what is actually occurring in the universe, I think what I like to point out with these sorts of diagrams is that if we're interested in studying these bulk flows, then we would do well not just to study the galaxies themselves, but also to look at the gas that surrounds them in the circumgalactic medium and use that in order to probe these baryon cycle flows that we think are so critical. All right, so if we talk about trying to observe these, we have a fair amount of evidence for galactic winds or feedback in galaxies, and a little bit less observational evidence, at least, of cold flows occurring. So I'll walk you through the feedback evidence briefly before I sort of move on to the meat of our talk. All right, so we have quite a few observations that demonstrate galactic winds occur. So we know that outflows, for instance, occur in the local universe in galaxies that have a sort of peculiarly high at redshift 0 star formation rate surface densities. So this is a beautiful photograph of M82 taken with multi-wavelength observations that illustrate a very large outflow coming from this galaxy. But more pertinent for the high redshift universe, which will be the focus of my talk, we can see very strong evidence for high velocity outflows in the spectra of effectively all star-forming galaxies in the distant universe. So this figure is from a paper from Chuck's 2010 paper. And here we're looking at a series of interstellar absorption lines in the rest frame UV of galaxies. And we're plotting them as a function of velocity with respect to the systemic redshift of galaxies. So plotted are a variety of ionized metal absorption features. And what we see is that they are systematically blue shifted with respect to the systemic redshift of galaxies. So this is strong evidence that winds are common in these galaxies because this material is flowing away from sort of the centroid of the galaxy. Now, from the same paper, Chuck used background galaxy sightlines to probe the circumgalactic medium and absorption. And what he showed is that these same metal absorption lines seen in the spectra down the barrel of the galaxy also persist, seen against these background sightlines, to relatively large distances. So that means that this metal material is likely moving out to distances of several tens of kiloparsecs, so relatively far into the dark matter halo surrounding these galaxies, out to distances that are sizable fractions of the virial radius. So as I was working on my thesis, we were interested in sort of probing this material in more detail. And I've continued that work after leaving Caltech. And so what I'm going to tell you about today is focused on looking at the structure of these metal absorption lines, but seen against a much higher fidelity probe, which is background quasars. All right, so the general schematic that I'll talk about today is mostly based on this concept, which is that we look for regions of the sky that have extremely high luminosity, quasars, such that a detailed spectrum of that quasar can give us a very precise mapping of neutral hydrogen and ionized metal species along the line of sight between ourselves and this quasar. We combine that with large galaxy redshift surveys, such that any galaxy where we have a redshift that lies in the foreground of the quasar, we can use this background quasar spectrum to probe this absorption at a variety of distances from these galaxies. And so try to build up a picture of what galaxies look like on average, but also ask questions about what the circumgalactic medium looks like next to a particular galaxy or set of galaxies. All right, so just a tiny bit more about this survey. So this is the first part of my talk will be based off of work from the Keck Baryonic Structure Survey, which is led by Chuck. This is 15 fields across the sky with some of the brightest high redshift, sort of redshift 3 quasars, such that the galaxies that lie in the foreground of these quasars probe this sort of cosmic peak in star formation. The spectra that we've acquired of these very bright quasars are really, really beautiful, and I'll show some in a moment. They have extremely high signal to noise and are very high resolution, and that means that we can make a really, really precise mapping of these various metal absorbers from the circumgalactic medium of galaxies. Now, this is combined with an extremely large, very densely sampled galaxy redshift survey around these quasar sightlines. And it's become quite impressive in overall size and number, but today I'm going to focus on an extremely small subset of galaxies from the KBSS, only 8 of them, where the background quasar sightline actually shoots through the virial radius of these galaxies, and so we're probing halo gas for this sample of galaxies. All right, so just very quickly, a little bit more about this galaxy sample, just so that you have some idea of what sort of galaxies I'm talking about. So generally, KBSS galaxies, because we're looking in the distant universe, these are galaxies that are relatively luminous within about a factor of 3 of L star at this redshift. They have ages anywhere from sort of a dynamical time scale in these galaxies up to sort of the age of the universe at these redshifts, and a pretty wide range of star formation rates, but all comparatively high than, say, something like the Milky Way. They have a wide range of stellar masses and sit in dark matter halo masses of about 10 to the 12 solar masses. That corresponds to a virial radius of about 100 physical kiloparsecs at these redshifts. And so that's sort of a good distance scale to keep in mind during the talk. All right, so jumping right in. The high redshift circumgalactic medium, what does the CGM actually look like in these distant galaxies? All right, so I'm a spectroscopist, so I'm going to be showing spectra to demonstrate what the CGM actually looks like. And so the schematic is what's shown here. We have a galaxy, and at 75 kiloparsecs away, we have a background quasar sightline that passes through its circumgalactic medium. And what I'm showing on the right is now the high-res spectrum itself, shown in black. It's been continuum normalized to remove any features from the quasar. And what we see in colors are the Voigt profile decomposition, a model of the absorption features in the circumgalactic medium of this galaxy. So there's 2 main points that I want you to take away from these relatively complex fits. So the first is that they are complicated, and that's because the circumgalactic medium of these galaxies is very kinematically complex. So this is just one of these 8 galaxies, but they are similarly complicated across the board. The other point that I want you to take away is if you look at the details of these bumps and wiggles, you can see that they appear to be similar across multiple ionization states. So these silicon-2 lines, carbon-2 lines, silicon-4, and carbon-4 lines all seem to have similar kinematic structures overall. However, we see a very different pattern, some very broad absorption lines in oxygen-6, which has the highest ionization potential of any of the species that we can measure with the sample. And so but interestingly, these oxygen-6 absorption features are at the same overall velocity scale as these other lower ionization species. Now, this is interesting because it points to the fact that you have gas that is almost certainly multi-phase. So you have likely somewhat higher density, cooler gas and lower density, quite possibly hotter gas observed in oxygen-6, and it appears in the same velocity range. And so this is exciting, I think, because this sort of structure can give us clues as to the nature of these absorption systems. All right, so, but one other thing that we want to sort of add into this picture is a discussion of how large these individual gas clouds actually are that are being modeled. So I didn't tell you a complete story of this galaxy. So at 75 kpc away, it does have a background quasar sightline passing through it. But we are very lucky in that for this particular quasar, it's actually gravitationally lensed. And so we don't have just one image, we have two images of the background quasar on which we can probe the circumgalactic medium. And so in a little bit more detail, at the redshift of this galaxy, it's at redshift 2.4, the two images of this quasar that pass through the CGM are separated by only 400 parsecs. And so at this distance of 75 kpc away from the galaxy, we can probe the detailed structure on 400 parsec scales of this CGM gas. So what do we actually see? Okay, so this is the same plot I showed you before. What I'm going to do now is replace the colored curve with the overall product of these Voigt profiles. So you see sort of a model of the brighter image of this quasar. And then I'll replace the background quasar spectrum with the fainter image of this quasar. So that's what's shown here. All right, so what we notice, first of all, is that overall across this 400 parsec difference, we see that the absorbers appear on sort of the same velocity scale. So the gas seems to have sort of some kind of coherent velocity field to it, and that's consistent across this 400 parsec range. Particularly in the oxygen-6 region, again, the highest ionization potential species that we trace with KBSS, we see that the profiles look essentially consistent, suggesting that the oxygen-6 structures, the structures that absorb in oxygen-6, are in fact larger than this 400 parsec scale. But when we look at all of these other somewhat lower ionization species, such as carbon-4 through silicon-2, we see strong differences between the two different images of the quasar. And what that tells us is that the individual structures that are giving rise to these individual absorption components are actually smaller than 400 parsecs. Now this added to the previous sort of discussion about the fact that these absorbers are kinematically complex and multi-phase, points to the possibility, or at least is consistent with the idea that this lower ionization gas could be small clumps embedded in a warmer volume filling medium that's largely traced in this case by oxygen-6, but might also be traced by other higher ionization species. And this is sort of consistent with the possibility that this is actually a galactic wind and we're just looking at it through absorption. Now, the small size of these circumgalactic medium clouds really presents, in my view, an enormous challenge to simulators. But I'm really hopeful because I think there's some novel approaches that are just sort of beginning to appear in the literature that I think are going to be promising for doing direct comparisons between these sorts of observations with theoretical models. So on the left, I'm particularly emphasizing work by Cameron Hummels at Caltech. So Cameron's really pioneered a new line of research looking at essentially the circumgalactic medium at much higher resolution. So he has coined the term enhanced halo resolution. And the idea here is that usually most of the resolution in these simulations is reserved for sort of the galaxy and ISM of the galaxy. But here he forces high resolution all the way out to the virial radius of these systems so that we can see the circumgalactic medium at sort of scales that are approaching some form of resolving these sorts of structures. It's not quite there yet. I think it needs a little bit higher resolution still, and that's what Cameron concludes in his paper. But I think these kinds of approaches are going to be needed if we're interested in actually doing any form of direct comparison. The right two panels are showing idealized wind simulations from Drummond Fielding and Evan Schneider. And here, because they aren't, these aren't modeled in a cosmological volume, these are idealized galaxies, they can actually look at winds coming off galaxies in extremely fine detail. And they see these extremely sort of minute structures that might be similar to the types of things that we're capturing with these data. And so I think that there's some interesting space here for doing more direct comparisons between observations and these sort of novel sets of simulations. All right, so moving on to sort of the next section of my talk, what are the physical conditions we're seeing in this gas in the circumgalactic medium, and what can that tell us about accretion and outflows? All right, so to talk about the physical conditions in this gas, I'm going to rely on the width of individual absorption lines seen in these quasar spectra, which tell us, which encode information about the overall kinetic energy in that gas. And it can tell us separately about the temperature of the gas, as well as bulk motions internal to these clouds, which I'll call during this talk turbulence. So these plots are meant to illustrate places in the data where I believe you can see these effects by eye. So first, I'll draw your attention to the left two panels, which are examples of thermal broadening in these spectra. So for an isothermal gas cloud, we expect that the energy of different particles are the same, and therefore the velocity of those particles are inversely proportional to the square root of the mass of the ion that's giving rise to this absorption. So what we expect is for a heavier ion, like silicon, shown here in green, to have an overall narrower velocity distribution than carbon, the lighter ion, seen in blue. And so we expect the profile of the heavier ions to be narrower than that of the lighter ions. And so these are cases in the data where I think you can see by eye that the carbon profiles are broader than the silicon profiles. And so these are examples of thermal broadening. The right-hand panels are meant to illustrate the opposite case. So these are cases where the width of the absorption line seems to be dominated by some form of bulk motion within this cloud. And in that case, the velocity is constant across different mass species. And so you expect the width of these lines to be essentially the same. And so these are examples where I think that can be seen by eye in the data. In practice, what we actually do is a detailed modeling of each of these absorbers with a chi-squared minimization code and pull out inferences of temperature and bulk motions or turbulence for each absorber that has that is observed in multiple elements with different sufficiently different masses that we can pull out this measurement. All right, so what do we see when we take a look at that? So this is a histogram of the gas temperatures found for gas within the virial radius of these KBSS galaxies. So I'll start by just saying up front that there are observational biases in this histogram, and in particular, using the UV absorption lines that we are studying with the KBSS data, we're not particularly sensitive to very hot gas. And so that oxygen 6 absorber is sort of the hottest phase of gas that we can trace, and gas that's at 10 to the 6 and greater degrees Kelvin, we really don't have a good probe for at this time. So this is not necessarily representative of the overall temperature distribution of gas in the halo, but it does show temperatures at which gas does exist. And that's actually extremely interesting because what these distributions show is that fully half of the absorbers that we see in the KBSS have temperatures between 10 to the 4.5 and 10 to the 5.5 Kelvin. Now that's not particularly hot, but it is hotter than what we would expect for random places in the intergalactic medium. And it's also significantly cooler than the virial temperature for these galaxies, which is closer to about 10 to the 6 Kelvin. This is also a particularly interesting sort of temperature range because this intermediate temperature gas sits right at the peak of the cooling curve. And so it cools very, very rapidly. And given that, the fact that this gas seems to be common in these distant halos means that warm gas is either constantly replenished or it's being heated by some process. Overall, this temperature distribution is consistent with this theoretical paradigm I painted at the beginning, where you potentially have cold filamentary accretion and then processes such as accretion shocks and outflows that could be heating the gas. So I think it's broadly consistent with this, but it also points to the importance of further study of this material if we're interested in constraining these processes. All right, so I told you in addition to temperature, we can also measure turbulent velocities internal to these clouds. So that's what's shown on the right. This is just a histogram of the turbulent velocities internal to these clouds. And you can see overall that they have relatively moderate turbulent velocities. To sort of put that more into context, we can look at the total internal energy inside these clouds and compare it to the thermal energy of the cloud. That's what's shown here. And we can see that the vast majority of absorbers in the sample are highly dominated by the thermal contribution to this internal energy. Another way to consider this is to think about the sort of Mach number of motions of particles inside these gas clouds. And what we see is that overall, the internal motions within these CGM clouds are largely subsonic. Now, this is potentially in contrast to the motion of these clouds through the actual circumgalactic medium. As you'll see later in my talk, many of these clouds are actually moving with very significant velocities, at least with respect to the systemic redshift of the galaxy. But nonetheless, the motions inside these clouds are really dominated overall by their temperature. All right, so coming back to this idea of gas temperature, this is another argument that perhaps looking more into these sort of warm absorbers might be particularly interesting. So this is again from Drummond-Fielding's 2017 paper, where he's really highlighted that overall the sort of temperature distribution of gas in outflows is at late times quite sensitive. In fact, the distribution at intermediate temperatures is quite sensitive to the parameters of the wind that he's inserted into these simulations, with significant differences being seen in high wind mass loading scenarios versus low wind mass loading scenarios. And so this is just really showing that this sort of intermediate temperature gas might be a very useful probe for studying galactic winds in the distant universe. Okay, so what do the simulations actually look like, and how are they doing in terms of matching these kinds of observations? Well, in reality, no one has really attempted to match these observations, and I think a more detailed look is required, but I wanted to give sort of a flavor of what people are seeing. So this is, I'm taking some results from a paper led by Zach Hafen, published last year, where he was looking at the suite of Fire2 zoom-in simulations. And I've just sort of pulled some information from this plot, which is in the appendix of that paper, to try and do a rough comparison between the KBSS data and what's seen in these Zoom simulations. So that's what I'm showing here. Again, the numbers are not exact, so just sort of pay attention to the overall shape of these pie charts. So what I want to highlight is that this intermediate temperature gas seen in orange seems to make up a roughly comparable fraction between the observations and these simulations. So perhaps this intermediate temperature gas is similar across the two simulations. The gray portion of these pie charts is higher temperature gas, but I already told you that we have some observational bias against detecting the hottest gas in these halos. And so maybe there's nothing really to speak of there. And the blue gas shows the somewhat cooler gas in the halos. I think the main issue in terms of this comparison is that when I plot these distributions of temperature, I'm plotting them by number. So this is the number of structures that we detect in these sight lines as a function of their temperature. And most theorists, when they plot these distributions, they plot them as a function of mass or volume. And so I think a more direct comparison between the data and these simulations are needed if we really want to take home something important from such a comparison. But I think overall, this looks relatively promising, and I'm hopeful that more direct comparisons in the future will sort of shed more light on this question. All right, so just to recap this section, I've showed you that gas exists at a wide range of temperatures in the halos of these galaxies. This very large amount of intermediate temperature gas points to the fact that the circumgalactic medium is dynamic, with constant heating or gas replenishment needed to keep this warm phase in existence. I think overall the gas temperature is broadly consistent with this paradigm of cold flows existing alongside warm gas from either outflows or accretion shocks. And I think if we want to disentangle and find evidence for outflows versus accretion shocks, we need to look more closely at both the kinematics of the gas and its chemical enrichment. All right, so moving on to the next section, I'm going to talk next about the kinematics of gas within the circumgalactic medium of these high redshift galaxies. And I'm going to ask first the question, can we detect inflows and outflows in the circumgalactic medium? And if so, what can the kinematics tell us about feedback? All right, so I'm going to start by showing you that we can, in fact, detect inflows and outflows commonly in these galaxies. And I'm going to do that by showing, by relying on redshift-based distortion. So this is just an illustration of what redshift-based distortions look like in the types of plots that I'm going to show. So this is the galaxy correlation function from the 2-degree field galaxy redshift survey. What's being plotted is the distribution of galaxies along the plane of the sky in the x-axis and along the line of sight in the y-axis. And you can see two principal anisotropies in this diagram that tell us about the motions, in this case, of galaxies with respect to galaxies. So first of all, we see a strong elongation at small transverse scales. This is referred to as the finger of God effect, and it's due to the very high velocity motions of galaxies that are very near to each other. On much larger scales, we see an overall compression in this diagram, which is referred to as the Kaiser effect. And this is due to the coherent infall, in this case, due to the collapse of structure that these galaxies sit in. Now, for what I'll show you, I'm gonna fold this in absolute values so that we have sort of the highest signal to noise we can. And I will not be plotting galaxies versus galaxies. I'll be plotting the correlation of absorption systems seen in neutral hydrogen and metal species with the positions of these distant KBSS galaxies. All right, so that's what I'm showing here. On the left-hand panels, I'm showing hydrogen gas, and on the right-hand panels, I'm showing metal absorption from Monica Turner's work, also analyzing KBSS galaxies. And so what we see are the exact same effects I was pointing out before. We see on small transverse scales, very high velocity gas, which is emblematic of what we think are likely outflows from these galaxies. Seen on megaparsec scales, we see the same overall compression, which is due to the coherent infall of neutral hydrogen gas due to sort of infall onto these structures. And we see generally a similar pattern in metals. Now, more recently, just this year, Yuguang Chen has presented a significant update to this. Yuguang used 200,000 foreground-background pairs that were assembled with this KBSS data set to significantly improve on this and look at much smaller transverse scales, which is a lot easier to do with background galaxies than with background quasars. And Yuguang spent a considerable amount of time modeling this distribution, and he showed that overall outflows seem to dominate the kinematics on small scales within this sort of virial radius, whereas cosmic accretion appears to dominate the H1 kinematics outside the virial radius. So I think this is generally painting the picture that these baryonic flows are common and can be detected in the circumgalactic medium. But I think that begs the question, does it matter? Are they actually impacting galaxies? So I thought I'd show you one sort of spectacular example where I think we can paint at least a pretty picture that perhaps these are significantly impacting galaxies. So this is an absorption system that's extremely rare, detected in the distant universe in molecular gas, so CO absorption, as well as molecular hydrogen, but is associated with an extremely high column density H1 system that also has a very large variety of ionized metal features that span 1,000 kilometers per second. An analysis of this absorption system carried out when it was first discovered in 2008 showed that this overall, this cloud of gas appears to have solar metallicity in addition to this, the fact that it is bearing these molecular species. Now, people had spent a considerable amount of time actually searching for the galaxy that gives rise to this structure using near-infrared integral field units. And I happened upon this system when I was doing sort of a wider field search looking for red galaxies around distant quasars to do a study of sort of more evolved populations in the distant universe. So this is the host, we believe, of this absorption system, or the reason why this absorption system exists. Doesn't look like much in this this 4-star photometry, but when we got a spectrum of this galaxy, it's really quite interesting. What it actually is a broadline AGN. So the spectrum on top is shown from the fire spectrograph on Magellan. We can measure the line width and see that it has something like a 300 kilometer per second line width, which is very atypical of sort of normal star-forming galaxies, and much more similar to compact AGN seen in the distant universe. It certainly sits on the AGN end of the BPT diagram, for those of you familiar with BPT diagrams, or also in the AGN cloud on the mass excitation diagram. And if we compare this galaxy's star formation rate to sort of typical star formation rates for galaxies of its stellar mass, we see that it appears to sit below the main sequence, so have lower overall star formation rate than would be typical for a galaxy of this mass. And so this sort of paints a pretty picture of perhaps this galaxy has actually flung out a wind of very high metallicity gas. This is massive enough that you would expect it to be able to produce solar metallicity gas. That actually contains molecules potentially. And so it's actually thrown out part of its interstellar medium and thus has a reduced star formation rate. All right, so this is one sort of spectacular case that we've seen evidence for, but is this common? Do galaxies commonly eject metal-enriched material from their systems? So here I'm showing the line of sight velocity distribution for all of those metal absorbers that I've been showing you from the KBSS sample within the virial radius, plotted as a function of the transverse separation between the sight line and the location of the galaxy. What I'm comparing this to is the overall escape velocity needed to escape from a halo with a overall dark matter mass that's similar to the ones that host these galaxies. And what's notable here is that for actually 70% of the galaxies in the KBSS that have detected absorption, those have, 70% of them have gas in excess of the escape velocity. And this is really quite remarkable. A large fraction of the KBSS galaxies seem to have metal-bearing gas that is likely to be completely unbound from these systems. All right, so what else can we say about this unbound halo gas? So here I'm plotting its velocity distribution as a function of the ionization state in which it's detected. We can see that it appears most commonly in high ionization gas, and it's not particularly commonly associated with high neutral hydrogen column densities. Sorry, I should say the dark blue histograms are those clouds that are formally unbound from the system. Okay, so it appears more commonly in high ions and doesn't seem to be commonly associated with large neutral hydrogen column densities. These two things together suggest that this gas is likely either highly ionized, metal rich, or potentially both of these properties. And it's not a particularly small amount of material either. So for the 5 galaxies that have unbound carbon-4, fully 20% of their carbon-4 column is formally unbound from these systems. Now, if this gas is due to outflows, it certainly represents metal-enriched material that would almost certainly be permanently removed from this galaxy. And so I think this is really pointing to the potentially dramatic effect that these galaxies can have, both on their further activity, but also certainly on the chemistry of these systems. All right, so that mostly closes off what I wanted to talk about in terms of this KBSS data set. I did want to point out that there is work ongoing modeling the ionization conditions within these clouds, and so that we can measure metallicities and gas densities to constrain masses. But for this KBSS sample, this ionization analysis is quite complex. And that's because we see very large changes in the ionization structure of these gas clouds on very small velocity separations. Most measurements of metallicities in the circumgalactic medium have been done averaging across the full circumgalactic medium of an individual galaxy. And so they produce one measure of metallicity and one measure of ionization. But the very complex structure that we're seeing in these clouds really require a much more significant and careful analysis. And so that's work that's ongoing. But I wanted to sort of paint a picture of how we might go about it by using another data set that I've been working on in collaboration with the Cubs team. So I'm going to argue that maybe we should start with sort of a simpler case study. So I'm showing on the left the same plot that I showed you at the beginning of my talk, one of the KBSS absorbers, and I'm comparing it here to one of the absorbers found at a redshift of 0.47. Now you can see that overall they have, similar absorption features, but the significantly lower complexity of these lower redshift absorbers may be helpful in terms of trying to determine a route forward for measuring the ionization structure of this gas. All right, so just a quick introduction to this survey. This is the Cosmic Ultraviolet Baryon Survey, or CUBS. It's a HST Cycle 25 large GEO program that's PI'd by Xiaowen Chen, myself, and Sean Johnson. It covers 15 quasars with the COST spectrograph on HST that are around a redshift of 1, so that we can use them as absorption probes to trace the circumgalactic medium of galaxies around a redshift of 0.4 to 0.8. So it's very similar to the KBSS, but instead of tracing galaxies at cosmic noon, it's tracing galaxies during the turndown in cosmic star formation. It covers 5 different ionization states of oxygen, which is sort of an interesting and novel aspect of the survey. And so that provides a new view of this very complex ionization structure that I was talking about in the circumgalactic medium. Now, just like the KBSS, this is paired with a large galaxy redshift survey that we have underway now. We've designed this as sort of a wedding cake strategy on the survey. So there's an ultra deep portion of the survey, a single pointing with MUs centered on each quasar, which gets us down to a limiting magnitude of 26 mag in our band. But we combine this with 2 large redshift surveys done with the LDS and IMACS on the Magellan telescopes, which give us a sort of view of the full virial radius and outer CGM of these galaxies, as well as the overall large-scale environment and clustering of galaxies with the IGM. So we've assembled a really awesome team to work on this, and today I'm mostly going to be highlighting work from some of our postdocs. The first 2 papers from the survey are both out. Xiaowen Chen wrote a paper sort of introducing the survey, and Aaron Batcher published a paper actually earlier this week on another molecular gas bearing absorber that we found in CUBS. But today I'll highlight work by Tom Cooper and Fari Zahedi, who are both postdocs at Carnegie. So I already showed this before. Tom has been studying the ionization structure of a small number of CGM absorbers to try and understand how we can best model them. He's demonstrated, in fact, that the abundances and ionization structure inside gas and CGM at intermediate redshift is, in fact, quite non-uniform. So here I'm showing the overall oxygen abundance as well as carbon abundance for 4 different velocity components within the CGM of this sort of sparse group that's detected at redshift 0.47. And we can see that across the 4 absorbers, there's that span a velocity range of about 200 kilometers per second. There's a factor of 10 in overall abundance variation, and that there appears to be some level of carbon enhancement in at least some of these components. Here's a plot sort of demonstrating that somewhat more clearly. This analysis is also ongoing for some other higher column density absorbers in CUBS. This is work led by Fari Zahedi. And here we're seeing evidence that, again, the abundance pattern in the CGM surrounding high neutral hydrogen column-density absorbers shows very significant variation. So here Fari's plotting iron on alpha as a function of the alpha overall metallicity in these absorption systems. And you can see that we have, for instance, 2 components that sit next to each other in velocity space that show, again, a wide range in the overall abundance and a wide range in their level of iron enhancement. And so we can look at the individual abundance patterns in these absorbers and try and tie them more directly to what might be occurring in these galaxies. And in addition to the fact that these absorbers show very strong variations in their abundance pattern, they also seem to trace very different environments, ranging anywhere from sort of single field galaxies that are relatively massive to populations of like a very sparse group of dwarf galaxies, up to relatively galaxy-rich groups. And so I think this is really pointing to the importance of contextualizing these CGM observations by studying the environments in which galaxies sit. And so I wanted to sort of conclude on this note, asking the question of whether we can use these same absorption line techniques that I've been discussing so far in this talk to also trace the impact of environment on galaxies at early times. So we know that galaxies' color, morphology, and star formation rate all correlate with the environment in which the galaxies sit. So here I'm showing plot from Peng et al. 2010 that was looking at the fraction of galaxies that are red in the SDSS as a proxy for quiescence. It's not a perfect proxy, but it's probably decent on this with this large of a data sample. Now, what they showed, and what has been shown in a lot of other work as well, is that it's not just the stellar mass of a galaxy that determines its colors or its probability of being quiescent, but also its environment, such that things that are in the highest level of overdensity in the richest clusters in the universe at low redshift are sort of equally probable of being quiescent as the most massive galaxies. But these sorts of plots beg the question, when environmental trends such as this set in. So we have some evidence that they persist out to about a redshift of 1, and past that, it's a little bit harder to say. In addition to this, we're interested in understanding why these environmental trends exist. So what processes actually most contribute to this environmental impact? So is it sort of a vanilla model in which you have the collapse of the highest density structures occurring early, and so you have sort of a faster processed set of galaxies in high density locations in the universe? Or are there particular physics that are common in high density regions that are important? So things like the deprivation of gas for feeding galaxies due to some combination of stripping or starvation, or things like increased galaxy interactions that occur either in groups or in clusters. And I think ideally, we would like to study these sorts of processes at early times when they're occurring and changing the ways in which these galaxies are forming or changing over time. And so this leads us to the idea of how we quantify environment in the distant universe. And I'm going to argue that finding dense environments, things like protoclusters at high redshift, is in fact really difficult. And that's because the structures that are going to collapse at redshift 0 into massive clusters are very large. They're like tens of megaparsecs at redshift 2.5. And so on the sky, that corresponds to a very large survey area, something like 20 arc minutes. Finding these dense environments in sort of generalized galaxy redshift surveys is complicated by that. And what people have often done instead is looked for sort of signposts of special environments. So they've used things like quasars or SMGs, unique special types of galaxies, to pinpoint environments that might be special. But the challenge there is, if that's the only way we can find them, then we sort of have put a prior on what the galaxies might look like in these high density regions. Similarly, people have identified structures in the distant universe by looking for an overabundance of particular types of galaxies in galaxy redshift surveys. But that's complicated by the fact that these surveys are often incomplete and they can be biased against certain galaxy populations. And so I wanted to ask the question of whether we can figure out a way to search for overdensities independent of their galaxy population, and in particular, whether these absorption line techniques can help. And so what I'll tell you about right now is a survey we have ongoing that uses the technique of IGM tomography to make a three-dimensional map of the distant universe. So to state it simply, neutral hydrogen gas in the intergalactic medium traces the underlying dark matter structure with pretty high fidelity. There's a really long literature about using neutral hydrogen absorption as this sort of proxy for overdensity or the underlying dark matter structure. Chuck, in fact, did early work on this, correlating Lyman-alpha absorptions with the overall galaxy density in the high redshift universe in collaboration with Kurt Adelberger and others in the early 2000s. But here what we want to do is, in fact, make this sort of three-dimensional map of the density field. And in this case, what we're going to do is use Lyman-alpha absorption that's detected against an irregular grid of unassociated background galaxies. So that's what this Lyman-alpha tomography is meant to mean. Now, a dream of tomography would be to map with multiple background sightlines the gas within a single galaxy circumgalactic medium. And that's in fact one of the major science cases for the 30-meter telescopes. But that requires a very high areal density of galaxies, which requires very sensitive observations of extremely faint galaxies. And so that's really the regime that we're talking about for 30-meter telescopes. But approachable now is a sort of typical sightline separation of about a physical megaparsec, which is what would be typical for bright Lyman break galaxies like KBSS galaxies. And this technique was actually demonstrated by KG Lee and the Clamato team which used LROs on Keck to make sort of the first such tomographic map of the distant universe. And we were really inspired by that work and recognized that a particular spectrograph on the Magellan telescope gave us sort of a bit of an unfair advantage in terms of speed of mapping. So the IMACS spectrograph on Magellan just has a very high A omega due to a very large level of multiplexing. We can observe 300 galaxies at a time. And so that means the speed with which we can make these maps is actually quite unique. So I'll tell you a little bit about this project, the Lyman-alpha Tomography IMACS Survey, which is led by Drew Newman, myself, and Guillermo Blanc, all at Carnegie, but with a large number of collaborators listed here. And much of this work at this point has been led by Drew, and so I'll mostly be presenting work that he has accomplished. So the main goal of LATIS is to map sort of a cosmologically representative volume around cosmic noon, centered about a redshift of 2.5 in the extragalactic legacy fields. So most of our volume is in cosmos. It'll cover overall about 2 square degrees on the sky, which corresponds to a co-moving volume of about 10 to the 7 megaparsecs. So that's large enough to include about 25 massive protoclusters that we think will evolve into clusters at redshift 0 with masses greater than about 10 to the 14.5. Drew put out a paper earlier this year, so if you're interested in the survey and want to see more details about it, I recommend going and taking a look at that. But just as sort of an advertisement, this is one of the maps that we made earlier last year, although we've acquired quite a lot more data since that time. And this is just to show you that we can make a 3-dimensional reconstruction of the density field. Red regions here show places that have significantly more Lyman-alpha opacity, which means they are much higher overdensity, whereas the sort of blue regions are more typical of the field. The bottom plot compares this overall density map with the locations of galaxies drawn from our LATIS redshift survey, as well as the VUDS and Z Cosmos. And what we can see is that overall, these galaxies appear to trace the LATIS density maps with relatively high fidelity, which is good. That's reassuring. So far, we've identified 27 structures in the LATIS volume that we believe have masses greater than about 10 to the 14 solar masses, and a larger number of low mass structures. And work is underway with Carnegie UCR graduate fellow, Maddie Keslu, shown here, who's working on determining how we can best measure the masses of these structures with the highest level of fidelity so that we can understand what their population looks like and study sort of galaxy evolution using them. But I wanted to give one sort of exciting advertisement for the work that's forthcoming. And that's demonstrating that tomography can identify overdensities independent of their galaxy population, and that might actually be important if we're interested in studying galaxy evolution as a function of environment. So here I'm showing a result that's sort of hot off the presses. We only found this about 3 or 4 weeks ago. And what I'm showing is the Lyman-alpha flux contrast. So this is sort of the figure of merit of the tomography survey, where regions with low contrast are relatively lower density regions, things like protogroups, whereas the regions over here at high negative values of Lyman-alpha flux contrast are the most massive structures we believe in these maps. The y-axis shows the density contrast, so the overall overabundance of galaxies seen in these particular structures picked out from the LATIS map. So that's what's shown in these black points. In green, I'm showing what the galaxy population would look like in a mock survey if galaxy evolution were unaffected by environment. And so we would see overall a larger number of galaxies in higher density regions traced by tomography. But what we see in the LATIS volume is, in fact, for the 6 highest Lyman-alpha contrast structures, the 6 structures that we believe to be the most massive in the LATIS volume, 5 of them actually appear no different than the population of field galaxies, which is shown in this blue band. So 5 out of these 6 most massive structures we wouldn't be able to detect in a galaxy redshift survey. And so this means that if we want a complete mapping of these structures, we need this sort of technique to find them. But I think even more excitingly, what this suggests is that the galaxies in these structures are likely already significantly impacted by environment. And this gives us a means to study this at early times. So there's a lot of work ongoing with LATIS trying to look at the spectra of these galaxies, these rest UV spectra, in order to understand what impact environment might have on the stellar populations that we're seeing in them, and winds and things of that sort. But a sort of future goal of this survey would be also to look at changes in their rest frame optical spectrum, which would require some sort of more advanced instrumentation. And so I'm going to end my talk by just talking very briefly about an instrument concept that's underway at Carnegie. It's an instrument called MIRMOS, the Magellan Infrared Multi-Object Spectrograph, which would be PI'd by Nick Conadaris, and Drew and myself are project scientists for. We're also working with two junior scientists who are extremely talented, Jason Williams, who's a graduate student at USC, who's doing his PhD at Carnegie, and Alicia Lanz, who did her PhD at Caltech and is now a postdoctoral fellow at Carnegie. So MIRMOS very much takes its inspiration from MOSFIRE, which, as Chuck mentioned at the beginning, I worked on as a graduate student and Nick worked on when he was a postdoc at Caltech. So we've taken our great love for MOSFIRE and tried to imagine a spectrograph that that builds on the success of that instrument. And so the idea is same as MOSFIRE, multi-object near-infrared spectrograph, but this would cover 4 bands simultaneously. So you have simultaneous coverage of the full near-infrared spectrum at a sort of comparable resolution to MOSFIRE, but over a larger field of view, 13 by 3 arc minutes. Now, interchangeable with this slit unit that is similar to the one on MOSFIRE would be an integral field unit, which would have an overall field of view of 26 by 20 arc seconds, which would be really world leading in terms of looking at sort of the volume with which you can study near infrared emission from the distant universe. All right, so highlighting why this might be important for something like studying environment, this is now showing one of the overdensities from the lattice volume and comparing it to the field of view of MOSFIRE versus the field of view of MIRMOS. And in particular, if we're interested in tracing multiple emission lines from these early galaxies, we need coverage of at least 3 out of these 4 bands. And so what this shows is that we would just have an increased speed with which we can survey the this sort of environmental impact in the distant universe. And as part of a proposal we put in to try and fund MIRMOS, we proposed a 45-night extragalactic program that I think is really exciting and would, I think, give us a new view of a variety of problems in galaxy evolution. On the right, I'm showing we would expect to get something like 2,000 star-forming galaxies at JWST GTO depth with this survey. But in addition to that, at the same time, with the same observations, just using the multiplexing of this instrument, we would also be able to get very deep spectra of about 400 reionization epoch galaxies, where we would be deep enough to not just detect Lyman-alpha emission, but also detect strong metal line emission from these galaxies and constrain things like their stellar populations. And then around cosmic noon also, we would be able to detect about 300 quiescent galaxies with sufficiently deep spectra to measure stellar absorption features to constrain things like metallicities and ages. So I think this is an exciting possibility for this instrument concept. Similarly, for people who are aficionados of KCWI, imagine an instrument similar to that, but put it in the near infrared. And that's sort of what we're looking at with MIRMOS. And I think that would have exciting possibilities for a range of science cases, but in particular, studying the kinematics of gas in the CGM using optically thin probes like nebular emission lines, I think would be one particularly exciting case. Okay, so that's MIRMOS in a nutshell, but if you're interested in hearing more about this instrument, I'd be delighted to tell you about it. But I just wanted to close with a quick run through of the conclusions, mostly from the first part of my talk. So I showed you that cool and warm metal-bearing gas clouds in the circumgalactic medium have relatively small sizes, less than about 400 parsecs, but that there appears to be a likely hotter oxygen-6-bearing gas phase that appears to be more volume filling. This is consistent with the picture where you have hot outflowing winds that carry along or potentially seed the formation of cooler, dense clumps. I showed you that the gas in the circumgalactic medium exhibits a wide range of temperatures. This overall has broad agreement with a general theoretical paradigm of cold flows existing simultaneously with outflowing gas or accretion shocks. And I showed you that there's a significant population of gas that's at intermediate temperatures. And given that this gas has a very short cooling time, it requires that the CGM is dynamic with constant heating or gas replenishment. And lastly, I showed you something about the kinematics of gas within the circumgalactic medium. Overall, that this shows evidence that inflows and outflows are common in these galaxies. I showed you that 70% of galaxies in our survey that have detected metals have unbound metal-enriched gas, and that the unbound metal-enriched gas appears to be more highly ionized and potentially metal-rich, which is again consistent with the plausibility that we're actually detecting outflowing winds from these galaxies. All right, so those are my conclusions. Just two really quick advertisements. We're hiring a staff scientist at Carnegie, the same position I have. It's sort of a faculty equivalent at Carnegie. So if you're interested in applying, I would be delighted to talk to you about that position. And also, I am the director of an undergraduate research program at Carnegie during the summer. We take SURF students. So if you have talented undergraduates at Caltech that you know, please feel free to send them my way. We're always delighted to host multiple Caltech students every summer. So I will leave my conclusion slide and take any questions. Thank you, guys.
Thank you, Gwen. Are there any, it looks like Catherine, you have a question?
Yeah, I was wondering if you could explain again how you measure that the clouds are 400 parsecs from the spectrum.
Let me pull up the slide for this again. All right, so here what we're relying on is the fact that for one of the galaxies that I talked about, the background quasar that we're using is in fact gravitationally lensed. And so we have two different images of the same quasar, which trace very slightly different paths through the foreground circumgalactic medium. And those two images at redshift 2.4, the redshift of this galaxy, are separated by 400 parsecs. And so what that means is that we have two distinct probes of the absorption, and we can look for differences across those two sightlines. And so when we look at the different sightlines, when we compare them, we see pretty significant changes in the shape of these absorption features across these two sightlines in the sort of lower ionization phases. And this suggests that the actual individual structures that give rise to single components that we're modeling have to be smaller than 400 parsecs. But that there appears to be this sort of potentially hotter or certainly more highly ionized phase that does not show changes over this 400 parsec scale. And so these are likely larger than that size.
Thank you.
Sure.
Let's see, Vikram.
Hi, Gwen. That was a great talk. Quick question on the sensitivity to high temperature gas. You mentioned observational biases. Could you maybe quantify that a little bit more and sort of say where roughly what the maximum temperature you think you're sensitive to is and how it fades off and so on?
Sure. So it's a little bit dependent on also the density. So it's not just a direct probe of temperature. And so what I can say directly is what we can actually probe is this oxygen 6. That typically is going to probe gas around 5 by 10 to the 5 Kelvin up to maybe 10 to the 6 Kelvin. But up past that, it becomes very, very weak. And so you're just talking about whether most of the oxygen is in this phase or in oxygen 7 or oxygen 8. And as you get to higher and higher temperatures, you really need a lot larger column of oxygen, regardless of what its ionization phase is, to be able to detect it. And so we're probably, if there is a very hot phase, we're detecting at best the sort of tip of the iceberg and probably gas that's cooling down from that very hot phase with these kind of UV absorption lines. Does that make sense?
Yep, awesome, thanks.
Lynn?
Yeah, I was wondering, relative to this plot, or relevant to this plot, but maybe more some of the earlier ones you were showing, how do you decide how many Gaussians or Lorentzians are enough to fit these profiles?
Yeah, that's a great question. So it's not a trivial process. It took a very long time to fit these, and I wouldn't even say that it's necessarily completely unique. So essentially, what the general ethos is that you penalize solutions that have a larger number of components. So you're only adding a component when the data really sort of require it. So formally, mathematically, it's a chi-squared minimization, but a lot of the actual fitting is somewhat finicky, and it's essentially looking, these spectra have signal noise upwards of 100, and so every little bump and wiggle in the spectrum is actually real. And so if you want to produce a good fit to these data, it does actually require a very large number of components. The modeling here is done with a particular sort of ethos, which is the thought that for gas at a given temperature and density, it should actually produce absorption across multiple phases. So you should see some amount of silicon-2 absorption, silicon-3, and silicon-4 absorption. And so they're actually modeled with the same component structure, which is not always done with sort of CGM or IGM observational studies. But if you're interested in modeling the components separately to try and understand their ionization structure, it's really makes the most sense to try and model them with this sort of like kinematic profile. And in this case, we have data that's high enough signal to noise that you can actually see and verify that that's actually a good model for the data.
So that's great. Can you say that again, though, with the, you're modeling the same species with the same number and kinds of profiles, or you're taking a temperature, say, and modeling across the species?
So what we're doing is we're basically lying down the same overall number of components, and we require that the width of the components is modeled with a single temperature and a single gas turbulence value for each kinematic component. So that's sort of the ethos of the modeling. And the only thing that can vary overall is the depth for individual species. They're often constrained by multiple transitions of the same ion, but overall they have to, the depth of individual species can vary. But the width of each component and its centroid location is determined by all of the different ionization phases in which such a component is detected. Does that make sense?
Got it. Yeah, thank you.
Monsi had a question, but wasn't able to raise her hand. But you're hereby allowed to ask your question, Monsi.
Thanks, Chuck. Thanks, Gwen, for a nice talk, as always. The question I had was, I was struck by your three-dimensional map from IMACS, I don't know, LATIS or something, I think it was called. And I was curious what the color coding there was, and was the size of the clusters in that, is that weighted by mass, or is that weighted by actual physical size? So if you could go to that slide.
Sure. This one?
Yeah, this one. Yeah. So are these mass, luminosity, physical size?
Yeah. So the actual number that's or the numeric value that's associated with the color coding here is actually the Lyman-alpha opacity, or really the relative Lyman-alpha optical depth compared to the average location in background galaxy sightlines. And so what we're looking at color coded in red are things that have a lot higher Lyman-alpha opacity. Now that might sound like a sort of random metric, but there's been a lot of studies that show a very strong correlation between the Lyman-alpha opacity averaged on large scales with the underlying dark matter distribution. And I don't have the plot in this slide, but I'd be happy to show you some other time that we've actually verified using mock surveys of sort of N-body simulations that have gas painted on them, that the expectations would be consistent for these. And we have work ongoing with a graduate student doing the same sort of verification using illustrious TNG. So using simulations that have baryons and baryonic processes, galaxy formation, et cetera, in them. Does that answer your question?
Yeah, thank you.
Nick, you have a question?
Yeah, just back where you had all the spectra before, back to the previous slide. I'm wondering what makes oxygen 6 so unique that we're seeing such a large spatial extent that it's covering this 400 parsec region, or 400 kiloparsec, sorry. And sure. Why are these lower ionization species, why are they in these smaller clouds, and what's causing the difference? Are these different physical processes, or are they coming from different sources?
Yeah, so I think we don't have a completely definitive answer for you on that, but I'll tell you the model I carry around in my head for this, which I think is fully consistent with these data, but there may be another solution that would also be consistent. And I'll use one of these sets of simulations to kind of show you what I mean. Okay, so here I'm showing these idealized wind simulations on the right. And what I think is going on is basically we're penetrating through likely an outflow from one of these galaxies, and the oxygen 6 phase is likely hotter gas. Right. And what some of this work by Evan Schneider and Drummond Fielding has shown is that when you actually throw out hot gas you can actually seed cooling processes, runaway cooling processes in hot gas actually seed very small, dense clumps that cool quickly and then would produce this sort of lower ionization gas that's at kind of intermediate temperatures. And so likely what's going on is that you have these broad oxygen-6 absorbers. They're relatively hot gas. And so that's why they're detected in oxygen-6, but also why they have these sort of broader line widths in part. And that's looking at sort of more of the volume filling part of what might be a wind coming out of these galaxies, with these small structures being little tiny seeded dense clumps that have fallen out of this hotter phase, or potentially could have been lofted, but that turns out, at least theoretically, to be challenging. And so I don't know whether it's more likely that this cooler gas is seeded out of hot gas or if it's actually pushed out of the ISM. The theorists, I think, would say it's more likely that it's seeded.
Yeah. That's what we're seeing on this plot on the right here. We're seeing those little cool pockets due to this runaway cooling effect.
Yeah, that's right.
Which could be where this lower ionization gas is coming from.
Yeah, so I think that's a possibility, certainly. If we had metallicity measurements, that would be a little bit more definitive, I think, because you would expect this gas to be hot. And so I can tell you that from sort of early analysis of looking at the ionization conditions in these galaxies, we do have detected some gas that has metallicities, sort of solar metallicity or potentially greater. And so that's consistent, certainly, with being from an outflow with these galaxies, being that that's actually higher than the overall level of enrichment in the interstellar medium in these galaxies.
Yeah, so then you definitely have a wind then. Yeah. Okay.
We should probably take one more question and then allow Gwen to rest her vocal cords. Let's see, Lee, you have your hand up.
Thanks, Chuck. Gwen, can you say anything about either the prospects or the prediction for detecting even slightly cooler gas below this sort of few 10,000 degrees, into the few thousand degree range where, we have to have a different kind of a probe? Is it even possible to detect that? What were the predictions for this gas sort of cooling out of these sort of smaller clumps that you're sort of detecting at a few times 10 to the 4?
Yeah, that's really interesting. So I don't think actually a tremendous amount about that, but my expectation value is that at least in some cases that would produce relatively high neutral hydrogen column density clouds. And so you'd be seeing them not as sort of Lyman-alpha forest absorbers, column densities of 10 to the 14 or 10 to the 16, but relatively higher H1 column densities. And so if that's the case, just based off of the sort of incidence of very high column density H1 structures, you would expect that they'd have to be enormously small, or else we'd have way too many of those compared to how many we have in the spectra of sort of galaxies and quasars in the distant universe. But there's also, of course, heating processes just from radiation and so forth. So for anything that's optically thin, you're going to have some amount of, you can't really get below a certain temperature floor easily unless you actually have shielding from the surrounding radiative field. And so that sort of sets part, at least in part, sort of a minimum floor until you get up to a high enough gas column density that you can sort of shield it from that radiation and it can cool further. At least I think that's the case. That would be my guess.
All right, thanks.
Okay, we should end the formal question period and